discover them. These strange laws that seem to contradict much of what we thought we knew about the universe. Not long ago, we thought we had it pretty much figured out. The rules that govern how planets orbit the sun. How a ball arcs through the sky. How ripples move across the surface of a pond. These laws were all spelled out in a series of equations called classical mechanics, and they allowed us to predict the behavior of things with certainty. It all seemed to be making perfect sense, until about 100 years ago, when scientists were struggling to explain some unusual properties of light. In particular, the kind of light that glowed from gases when they were heated in a glass tube. When scientists observed this light through a prism, they saw something they'd never expected.
If you heated up some gas and looked at it through a prism, it formed lines. Not the continuous spectrum that you see projected by a piece of cut glass on your table, but very distinct lines.
It wouldn't give out a smear kind of complete rainbow of light. It would give out sort of pencil beams of light at very specific colors.
And it was something of a mystery how to understand what was going on.
An explanation for the mysterious lines of color would come from a band of radical scientists who at the beginning of the 20th century were grappling with the fundamental nature of the physical world. And some of the most startling insights came from the mind of Niels Bohr, a physicist who loved to discuss new ideas over ping pong. Bohr was convinced that the solution to the mystery lay at the heart of matter, in the structure of the atom. He thought that atoms resembled tiny solar systems, with even tinier particles called electrons orbiting around a nucleus, much the way the planets orbit around the sun. But Bohr proposed that unlike the solar system, electrons could not move in just any orbit. Instead, only certain orbits were allowed.
And he had a really surprising and completely counter-physical idea, which was that there were definite states, fixed orbits that these electrons could have, and only those orbits.
Bohr said that when an atom was heated, its electrons would become agitated and leaped from one fixed orbit to another. Each downward leap would emit energy in the form of light in very specific wavelengths, and that's why atoms produce very specific colors. This is where we get the phrase quantum leap.
If it weren't for the quantum leap, you would have this smear of color coming out from an atom as it got excited or de-excited. That's not what we see in the laboratory. You see very sharp reds and very sharp greens. It's the quantum leap that's the origin and the author of that sharp color.
What made the quantum leap so surprising was that the electron goes directly from here to there, seemingly without moving through the space in between. It was as if Mars suddenly popped from its own orbit out to Jupiter. Bohr argued that the quantum leap arises from a fundamental and fundamentally weird property of electrons and atoms, that their energy comes in discrete chunks that cannot be subdivided, specific minimum quantities called quanta. And that's why there are only discrete, specific orbits that electrons can occupy.
An electron had to be here or there and simply nowhere in between. And that's like nothing we experience in everyday life.
Think of your daily life. When you eat food, you think your food is quantized? Do you think that you have to take a certain amount of minimum food? Food is not quantized. But the energy of electrons in an atom are quantized. That is very mysterious. Why that is?
As mysterious as it might be for tiny particles in an atom to act this way, the evidence quickly mounted showing that Bohr was right. In more and more experiments, electrons followed a different set of rules than planets or ping pong balls.
Bohr's discovery was a game changer.
And with this new picture of the atom, Bohr and his colleagues found themselves on a collision course with the accepted laws of physics. The quantum leap was just the beginning. Soon Bohr's radical views would bring him head-to-head with one of the greatest physicists in history. Albert Einstein was not afraid of new ideas. But during the 1920s, the world of quantum mechanics began to veer in a direction Einstein did not want to go. A direction that sharply diverged from the absolute definitive predictions that were the hallmark of classical physics.
If you asked Einstein or other physicists at the time what it was that distinguished physics from all kind of flaky speculation, they would have said it.
All right, it's time to say goodbye to stubborn fact. We have something that just might allow this to actually happen.
Oh, you gotta stay tuned for this one. Belize Metzval invited us to its downtown location and showed us how cool sculpting works to freeze away that unwanted fat. You no longer have to fear maybe wearing that tight little dress that you like, or for some men, maybe wearing the tight shirt, because we have a procedure here at Belize Metzval that you're going to want to be a part of. Cool sculpting. Jamie Tycho joins us now with what this is all about. Sounds cool, and it literally is done. It literally is, because it does some really cool stuff to your body.
It does, yes. So what cool sculpting is, it's a completely non-invasive procedure that we offer here at Belize. And it actually freezes the fat, and it's a fat-reducing treatment that we offer. Completely no downtime. And yeah, it just, what it does is actually freezes the fat cells, and about 22 to 25% of those fat cells are naturally processed. It takes about 2 to 3 months to see some great results.
But it's a start, and would you recommend if somebody coming in for a free consultation?
Correct, yes. We do want to do a personal assessment for each individual person.
Because you have to actually touch the client to figure out where you're going to start the sculpting once you actually visit with them.
So we have small heads and large heads, those applicators. So coming in to actually see exactly where we need to, do it if they need a large head or a smaller one, applications.
And so can you do it in different parts of your body? Where would you cool sculpt?
So anything that kind of really targets those areas that you want help with, just, exercising and diet just isn't helping. This is this alternative way to help reduce those fat in those areas. Of course, we get such great results from the abdomen area. But yes, we can do inner thighs, outer thighs, banana roll behind the legs. We can do underarms.
Hey, it's just all inclusive. And so where do you start? You study when somebody comes in and you've already done the consultation. They come in, you're very protected with this. You have a cool gel that you use or a cool pack.
Correct.
It starts, because is the abdominal area the predominant area that people come in for?
It's very popular. That's probably our most popular, best results we see in this procedure as well.
How long would it take? Let's say I come in. I already come into my consultation and I want to get the ab area worked out. How long would it take for someone?
It's an hour per area. So per applicator takes an hour to actually sit there. We get you as comfortable as we possibly can.
And this is a machine?
This is the machine.
What does it do?
It does. So what we do is we are going to have our client, patient come in. We actually look at the area of concern. So let's say her lower abdomen is her area of concern. This is the cooling gel pad that we will use. This is what protects the skin from the actual machine. So we place that cooling pad on there, and then what we do, whether it be the smaller head or the larger applicator, that's when we actually place the head on the area being treated, and it kind of feels almost like a suction cooling sensation. And at